Okay, thank you, John. And thank you to the organizers for the opportunity to talk. It's been a really nice program so far and a really nice week. Okay, so I want to talk to you about my perspective on synthetic spectra, which is very much influenced by a collaboration I have at the moment with Christian and Sven van Nichteweg. So Christian is just over here, and Sven will be here later in the program. So if you want to talk about any of these things, feel free to talk to me or all three of us. We're all eager to share what we've learned about this recently. Okay, so I want to cut my talk up into 3 little digestible chunks. In the first bit, I just want to give you a bit of setup. So I want to tell you about synthetic spectra. I'll do this in a very sort of axiomatic way, like here's a category, a bunch of functors, and here's how you can construct what you need to construct. And then I want to define what I mean by a signature. So a signature is going to be a spectral sequence associated to a synthetic spectrum. And at the end of the day, I'm more interested in these signatures than the actual synthetic spectra themselves a lot of the time. And then in part 2, I want to look at a bunch of examples. So I want to do 2 things with these examples. They're going to be examples of signature spectral sequences. The first thing I want to show you is that there's just a lot of them. So there are a lot of spectral sequences that you've already come across in your everyday life. Well, a lot of you every day and some of you sometimes. And I'd like to show you not only how many there are and how varied they are, but also how flexible they are. So they're kind of quite malleable. You can sort of manipulate these spectral sequences to do what you want to do to a degree. And then in the third part, I want to really dive into some applications to detection. And I find the story so straightforward and pleasant that I would like to start at height 1 and really just give a sort of blow-by-blow argument of sort of detecting V1 periodic families in the sphere using signature spectral sequences associated to synthetic spectra, which you have constructed exactly for this purpose. And then I just want to talk about some recent ideas that me and Christian have had that work at the height 2 as well. Okay, so let's get started. Okay, so for this part of the talk, we're just going to let E be some atoms type homology theory or spectrum. So think anything where you have a reasonable E-based atom spectral sequence. Then you can define an infinity category of spectra, infinity category of synthetic spectra. And of course, it's going to have all the usual lovely adjectives. So this is going to be stable, it's going to be symmetric monoidal, and it's going to be presentable. So in particular, you can do all of the normal sort of operations and constructions that you're used to in spectra. So there's an infinity category of synthetic spectra. So I'll write as syn with a base E. The definition is not so hard to give, but I also find it not necessarily very enlightening. You can define it as some category of product-preserving sheaves with values in spectra on a category of spectra which have finitely presented E-homology. And there's a certain Grothendieck topology you're putting on this category of sheaves, but like I said, it's not super important for what I want to do. I want to describe how to work with this category, not necessarily how to define it. But you can see from the definition that it probably has all of these properties. Okay, so there are 2 or 3 really useful functors that I want to consider in conjunction with this. The first one is a synthetic analog functor. And what this is it's some sort of infinite delooping of some Yoneda embedding. So it's maybe quite plausible that something like this exists. And there's inside this category of synthetic spectra, I'll define in a moment, there is a map called tau. And well, what can you do if you have a map in a category? Well, you could look at the category of tau local things, and you can look at the category of things where you kill tau. So there are going to be two functors, one of them where we invert tau, and one of them where we sort of quotient out by tau. And they're going to land back into two categories that we should be a little more comfortable with. The first one is spectra. So in fact, we have a sort of commutative triangle like this with the identity at the bottom. And what's happening over here is when we take a quotient by tau, we're ending up in some derived category of E star E comodules, some stable infinity categorical version of that. So the takeaway is that if you have a synthetic spectrum, you could invert tau to recover the underlying spectrum, or you could kill tau to get some algebraic object. I'm going to think of synthetic spectra as being like spectral sequences, and this inverting tau is going to be like what this spectral sequence converges to, so the abutment, and this killing tau is going to give me the E2 page. So if I understand these two functors, then I can understand the beginning and the end of the spectral sequence, hopefully work between them. Okay. That's coming up. Yes, so now I just want to give you a collection of facts. The first one is that if you take the synthetic analog of the sphere spectrum, you end up with something that I'm just going to write as S00, and this is the unit of this symmetric monoidal infinity category here. So is the unit of syn E. This will be important later, so we'll see this fact come up a little bit later. The second thing is that this synthetic analog functor, it doesn't preserve all limits and colimits or something like that. And rather than complaining about this, you can sort of use this to your advantage. So you can use this to actually define this map tau. So nu does not preserve cofibers. And in fact, so it means in particular, it doesn't preserve suspension. So if you take the synthetic analog of a spectrum and you take the suspension inside the infinity category, which is synthetic spectra, then this is going to admit a canonical map to the synthetic analog of the suspension of X. But in general, this won't be an equivalence. And in particular, it's not going to be an equivalence when you apply it to a sphere. So what's the usual thing to do? You slide that down, and then I slide the other one up. Great. So if I plug in a certain value of X here, I'm going to get a definition of this tau map, which I claim to be so important. So we can define tau as the thing that goes from suspension of nu of the -1 sphere mapping to nu of the sphere. So there's just a suspension on the inside, which I've been playing with. And this guy, like I said, is just this synthetic unit here. And this guy, I'm going to define with this sort of bigrading. So I'm going to define it to have bigrading 0, -1. So you want to think about this tau as always reducing the bigrading in the right-hand variable, by 1. Okay, so this is how you define this tau map, and you can now use, you can now define these bigraded suspension in general. So general. And I just want to give you some formulas so that you can see that they're not too confronting, even if they maybe don't speak to you right now. So you can just define this as the smash of SF tensor with X, which by definition is just with F matched with X. Okay. So you might ask why we do things in such a complicated, well, with such a complicated grading, because this isn't exactly how it's done in Pestrovsky's original paper. But the reason why I like this grading and why I call it S and F is that the spectral sequence associated to synthetic spectra is going to have, the S grading is going to be the stem grading, and the F grading is going to be the filtration. So I find it very convenient to use this sort of grading mechanism. In fact, without it, I think I would be very, very lost. Okay. So here are some definitions. Okay. I think we're okay for now. Now I want to define what this signature is. And John's right, it comes exactly from some sort of Bockstein. So let us write fill SP for the infinity category of filtered spectra. So this is just the functor category from Z op into spectra. Objects in here really are spectral sequences in the same way that a filtered chain complex gives you a spectral sequence. In the exact same sort of way, every object in here has an associated spectral sequence. So I'm not going to necessarily write down a spectral sequence with an exact couple or something like this. I'm just going to construct a functor from synthetic spectra into the filtered spectra. So we define a functor sigma, which goes from E synthetic spectra to filtered spectra as follows. It takes your X and it does the following. So the nth level of this filtered spectrum is going to be exactly the mapping spectrum. Let me write this with a little more clarity. It's going to be the mapping spectrum from, this is also where I need to be careful with my gradings, from the 0 minus n sphere into X. And what are the boundary maps going to be? What are the connecting maps going to be between these different things? It's just going to be the tau multiplication. So tau multiplication in this variable is going to reduce in this direction. So then the thing to go here is minus n plus 1 of X, which is the sigma n plus 1. Okay, so this is how I define my functor from synthetic spectra to filtered spectra. In other words, I'm going to call sigma X the signature of a synthetic spectrum. Make that a definition. Okay. Are there any questions at all so far either? Yeah. Fantastic. Is this the right direction? Is that really what I want to do? I mean, it either works or it doesn't work, and it's the. I know. I mean, Z with the usual ordering, sort of the numbers go up, but I'm looking at Z op, so it should go down. So I want these to go down to -1, and so I would like it to be what I had before. I think I would like it like that. Yeah. Okay. Good. I heard a vague no, and it caught me. It was exactly the reason why I wrote this down in details in my notes. Okay, so the signature spectral sequence of X is the spectral sequence associated to this synthetic analog. This signature, the signature of X. And so what form does this take? Well, the associated graded is going to be what happens when we take all the cofibers of multiplication by tau. So the E2 page is going to start like this. It's going to start with the bigraded homotopy groups of X where we've taken the quotient by tau. And remember that this was some algebraic thing. This was something living in this category of comodules. So this was something totally algebraic. I mean, maybe the brackets should be here because I mean, homotopy groups are always algebraic. It's the spectrum object here that's algebraic that's important. And so what does this converge to? Well, it converges to what happens when you take the co-limit along this. And the co-limit along multiplication by tau is what happens when you invert tau. So this converges to pi s of X with tau inverted. So this is the signature spectral sequence associated to a synthetic spectrum. It's not exactly a Bausfield-Kahn. There is a Bausfield-Kahn internal synthetic spectra where you have like a trigraded thing. Sometimes is useful to deal with, but we won't need that today. I didn't want to highlight that. Okay. Yes, actually, maybe just let me repeat that. For this talk, I'm mostly interested in this spectral sequence, this signature spectral sequence, but there are many, many reasons why actually working with the synthetic spectrum X gives you a lot more data than just working with this spectral sequence. There's a lot of tricks that you really require to have the sort of this deformation, this actual synthetic spectrum, and not just dealing with this spectral sequence. But today, this won't play too much of a role. Okay. Great, I got that on the board. That was the first thing I wanted to do. Now I want to look at some examples. Okay. So the first example, and I'll start putting some names here because the whole setup of synthetic spectra is due to Piotr Przestrogowski, and a lot of the work after that is due to is an appendix of a paper by Birkeland, Hahn, and Sanger, and that's who I want to attribute this first example to. So to Piotr, Birkeland, Hahn, Sanger, is they computed what the signature spectral sequence associated to a synthetic analog is. So in other words, they computed, roughly speaking, what this guy is, what this sequence of Greek and Roman letters is. And the answer is, this gives you the E-based atom spectral sequence for X. Up to, let's assume that X is E-nilpotent complete. So in this sense, the synthetic analog functor is a functor that sends a spectrum to this synthetic analog. So it's sending a spectrum to its E-based atom spectral sequence. And then when you kill tau, you're ending up with the E2 page of this. So just the classical E2 page of the E-based atom spectral sequence. And if you invert tau, you're recovering your spectrum back. And so because of a result like this, we like to think about the whole category of synthetic spectra as somehow being a category of modified E-based atom spectral sequences. So the whole category of modified E atom spectral sequences. And so what do I mean by this? I mean that there can be lots of different synthetic spectra who converge to the same, whose associated signature spectral sequence has the same abutment. So lots of different synthetic spectra which have the same underlying spectrum after tau inversion. but which might have very different associated signature spectral sequences. So anything that's not of this sort of standard form that looks like it comes from a synthetic analog, we sometimes call like a modified atom spectral sequence. Of course, there's a universal example that I want to just highlight as well, which is that the signature spectral sequence associated to the unit is, well, by definition, this is the synthetic analog of the sphere. This is just the classical E-based atom spectral sequence for the sphere. So it's telling you that since this is the unit in the category of synthetic spectra, every time you have an algebra object in synthetic spectra, it receives a unit map from this unit, and so the associated signature spectral sequence is going to receive a canonical map from the E-based atom spectral sequence. And this is a very, very useful trick. Okay, so that's our first example. Yeah.
Your map to this sigma xn, you're mapping from S naught comma n. Or you're either tensoring with S naught comma n in the target, or you're mapping from S naught comma n.
So I think I'm mapping, like, I mean, the map is going in this direction.
Increases the second index by 1.
So
you're mapping out of it.
Of course you would notice.
Sorry, 0n and 0n plus 1.
0n and?
Yes. You need 0n minus 1.
I'm trying to think of the most diplomatic way to deal with this. Because yeah. Maybe the most important thing is that the spectral sequence looks like this. And the most important thing for me personally is my co-authors as well, because they definitely help me with this.
You didn't say which way the direction when you I guess.
Yeah.
You don't have to.
No. Let me do that. So they should go from. Oh, let me just write it down. Ah, you're being very distracting. So they, of course, decrease stem by 1 and then the filtration by R. So it's sort of with the atoms convention. Yeah. Sorry. Okay, so that's one example. It's the simplest example. It's but just like many simple examples, it's like the fundamental canonical example as well, prototypical example. Okay, the second one I want to mention is due to me and Christian and Sven, but actually it's kind of a reworking of something that's been known for a while. So in this case, I want to take E to be mu. So I would like to work in mu synthetic spectra, and I want to think about everything as being like a modified Adams-Novikov spectral sequence. And in this case, if A is a Landweber exact E infinity ring, you can loosen some of these adjectives, but this is okay for now. With a G action by a finite group G. So the sort of examples I'm thinking of are like Ku and ENs. Ku, of course, with the usual C2 action. ENs with some finite subgroup of the Morava stabilizer group action, or you might consider some TMFs with level structure or something like this.
That's complex computational.
Yep. Yes, of course. Well, with this action. Okay. Okay, so this is a setup. And what can you do? Well, you could take the synthetic analog of this spectrum. So you know that the underlying, you know that the signature of this synthetic spectrum is just going to be the Adams-Novikov. And this is going to be very boring because my guy is Landweber exact. So in particular, it's complex oriented. It's just going to be concentrated in degree 0. But now what happens if I take the homotopy fixed points in the category of synthetic spectra? So I'm not taking my homotopy fixed points and then taking the synthetic analog, but rather doing it in synthetic spectra. And then the theorem that we wanted to state was that this is actually the homotopy fixed point spectral sequence associated to this G action on A. I actually wanted to include a different example, but then I remembered I was at this Equivariant conference and I thought I needed to give something with a few more groups, a few more group actions. The what? Oh, you mean this guy? Yeah. No, it's really like if you were working in the category of, in synthetic spectra. So we're really not thinking about this as being a chain complex, like a filtered spectrum, but really a synthetic spectrum. And then you take the homotopy fixed points, you just take the limit of the G action in synthetic spectra. Sorry, thank you. Very good. And then I mean equals in the way I mean it over here. A bit of a loose way. Yes, thank you. Okay, yes, and so you get this homotopy fixed point spectral sequence. Now, of course, you could permute the order of this, and you could consider what happens when you first do the homotopy fixed points and then apply the synthetic analog. But we already know what this does. This is just the Adams-Novikov spectral sequence for these homotopy fixed points. Then we apply this. But you can see that there's always going to be a canonical map in this direction, just the synthetic analog limit exchange map, assembly map. And sometimes this map is an equivalence, and sometimes it's not. So we also give a list of criteria when this is an equivalent. So for example, it is an equivalence in this situation, for example. So this is a proof of the classical fact that if you run the Adams-Novikov spectral sequence for KO, you end up with something that looks exactly like the homotopy fixed point spectral sequence for KU with the C2 action. Okay. But oftentimes, this map is not an equivalence. And I think this is where synthetic spectra really come into their own, because I claim that the Adams-Novikov spectral sequence for this is usually a lot more work and a lot more hassle than just trying to compute the homotopy fixed point spectral sequence. The homotopy fixed point spectral sequence is given to you compute some group cohomology. It's usually much easier than trying to compute these X groups of these BP star BP comodules. And but if you phrase everything in terms of synthetic spectra, you still have a unit map. So you still have a map from the signature of, from the signature of the synthetic analog of the sphere. So you still have a unit map coming from the Adams-Novikov spectral sequence of the sphere. So even if I didn't know this map was an equivalence, I still get this really useful map from the Adams-Novikov to the homotopy fixed points that'll help me with detection. For example, this, hopefully we've all seen this example of this homotopy fixed point spectral sequence for KU, and part of the whole point of this spectral sequence is detecting eta. And the key thing is once you've detected eta, you're fine. And you can do this in lots of different ways, but using a map like this, you can do this in a very, it becomes very, very sort of rudimentary, very sort of straightforward. You can prove that this detects eta. You don't have to check Kobar representatives or something like this. Okay. The third example is also by the three of us. And this is what happens. So let's take E equals mu. And I'm just going to write this one down quickly. So when you define something like the global sections of a spectral stack, then you might end up with something like TMF. So TMF is, by definition, the global sections of this sheaf on the moduli stack of the compactification of the moduli of elliptic curves. But another way to think about it is as a limit over a certain cosimplicial diagram given by some complex-oriented E-infinity rings like this. So these are all complex-oriented Landweber exact E-infinity rings. And now you can do the same sort of process you have here. You can ask yourself, okay, well, what happens if I first take the synthetic analog of TMF, or, and then of course, I'm going to ignore the sigma for now, or if I look at the limit inside synthetic spectra along this same diagram where I've post-composed with this synthetic analog. And this was a recent paper of ours where we studied this guy in detail. We called this guy synthetic modular forms. And in one paper, we could check that this map is not an equivalence. This is another classical fact. And for us, computing, I haven't told you what this is yet. But for us, computing the signature spectral sequence associated to this guy was much better behaved than computing this Adams-Novikov spectral sequence. In fact, we made lots of arguments that we don't know how to compute the Adams-Novikov spectral sequence here, but we do know how to compute this guy, which happens to be the descent spectral sequence for TMF. So in other words, if you have something that's constructed as the global sections from some spectral stack, then permuting the order in which you take your limit or take synthetic analog often moves you between the Adams-Novikov for the global sections and the descent spectral sequence. Okay. So I don't usually like to talk when I arrays so everyone can have a chance to digest, but Ben will give a talk in a few weeks where he'll talk about this in a lot of detail. There's lots of neat tricks that you can do when you're trying to compute this descent spectral sequence, but we're going to go in a different direction today. Okay, I just want to give you two more examples, and these are going in a bit more of a surprising direction, and these are both due to Christian. The first one is that if you work in mu synthetic spectra and you look at the signature spectral sequence of the following formula, you look at BPN, you take its synthetic analog, you take the homotopy C2 fixed points in synthetic spectra, and then you do some sort of strange connective cover, so there's some exotic T structures in synthetic spectra, then, well, if I explain to you what this T structure was, it's really just taking a spectral sequence and cutting it along the x equals y axis and discarding everything to the left. Then, then this formula makes sense as a synthetic spectrum, and the spectral sequence associated to this is the slice spectral sequence of BPRN. So I find this quite surprising. Another thing you can do, which is also rather bizarre, is you can sort of do a variation on this theme. You can have a look at what happens when you take connective Ku, take its synthetic analog, you take these homotopy C2 fixed points, and now you take another type of connective cover, but which we call the vertical connective cover. So not where you cut along the x equals y axis, but when you cut along the vertical line. Makes sense. and then you take the synthetic analog of that, you end up with something that is it's some sort of combination of the May spectral sequence and the atom spectral sequence for KO. Which looks very similar to a spectral sequence by Mike and Tyler Lawson. And maybe I shouldn't say equal, I should say it looks like. So there is sort of, there's lots of flexibility in this category of synthetic spectra. It's because I don't know, and I think it's not clear how to compare them directly. But
in that they both start on the May 1 page.
Okay, so they're the same in flavor. Yeah, very good. Okay, great. So now I want to get into some applications with some of these spectral sequences, because I've just sort of thrown them all at you now, and now I want to show you that if you start with some simple ones, you can start to build some fun examples.
So the decorations on the tool refer to two different T structures.
Yeah. Yeah, so basically every time you look in synthetic spectra, you can define some T structure given by a line or something like this, where you basically, the connective cover is given by sort of cutting your signature spectral sequence along that line and throwing out everything to the left, roughly, as long as there are no crossing differentials. And you can define these T structures, and you can do it for the x equals y axis for mu, because you have this vanishing line for the Adams-Novikov for the sphere. But because the F2 based atom spectral sequence has this H0 tower, you can only take vertical covers. You cannot sort of cut these towers off, or at least, yeah. Yeah, I am here. Okay, so let's start at the prime 2. So if we want to compute something like height 2 periodic families, like V1 periodic families, then we probably want to start with KO, and we probably want to take Adams' suggestion by looking at KO equipped with Adams operations. So we can look at the Adams operation psi3, and we can look at the fiber of psi3 minus 1, so the equalizer of psi3 and the identity, and call the fiber of this J. This is what's called the periodic image of J spectrum. Okay, so, I mean, KO receives a map from the sphere, and the unit is clearly mapped to 0 in here because psi3 is a ring map. So we're just going to factor through here. In fact, you can rig up this, well, in fact, if you view J as an equalizer of these two maps, then it's also an E infinity ring. And so you can ask questions like, how much of the stable homotopy groups of the sphere does J detect? What is the image of this unit map here, this Hurewicz map? Keep in mind that it's very easy to compute the homotopy groups of J. There's no questions here. You know the homotopy groups of KO, and to compute the homotopy groups of J, you just run a whole bunch of long exact sequences. Yeah. It's, however, much less clear how to compute this Hurewicz image. So you can compute exactly what these homotopy groups are, but you, of course, don't know what all the homotopy groups of spheres are. So you don't a priori know how to, this question might seem quite difficult a priori. And one thing that spectral sequences are really useful for is making sort of detection statements like this. For me, if you have a map between two different spectral sequences, it's easier to argue what the image of one bigraded thing looks like in the image of the other bigraded thing, rather than if you just have a look at what happens on homotopy groups. But then we have a problem because we want to try to compute not just the homotopy groups of J, but we actually want to compute a spectral sequence associated to J. We would like some sort of Adams or Adams-Novikov, well, not Adams because it's periodic. We want some Adams-Novikov spectral sequence associated to J. But I claim that that's very hard to do, to try to compute the Adams-Novikov for J. In fact, if anyone can tell me of a reference where something like this is done, that would be really nice. So maybe this parentheses means it's hard, at least for me. But what can you do? Well, you can try to construct a synthetic spectrum whose signature spectral sequence converges to the homotopy groups of J, which does have a very manageable structure. And so you could try the following thing. You could have a look at the synthetic analog of KO. You can look at this psi3 minus 1. You can look at the synthetic analog of KO. So I'm just taking the synthetic analog of this diagram. And now I can, rather than taking the synthetic analog of J, I can take the fiber in synthetic spectra. So I'll call this J sub mu or something like this. So this is, consider this by taking a fiber in mu-based synthetic spectra. Okay, so what does this give you? Well, let's just try to compute the signature spectral sequence associated to this guy. So what is it going to be? Well, the E2 page is going to look like pi SF of J mu mod tau, and it's going to converge to pi s of J mu tau inverted. So the first thing to notice is that this tau inversion, I mean, this is localization. It commutes with, well, it's exact at the very least. So in particular, it's going to commute with taking this fiber here. And so this is going to be exactly pi s of J. So in other words, we're converging to the correct thing. Now we just need to ask ourselves how we're going to compute this E2 page. Well, how did I claim that we computed the homotopy groups here? We just looked at a long exact sequence. So to compute the E2 page of this guy, let's just look at the long exact sequence coming from this fiber sequence in synthetic spectra. So to compute the E2 page, recall that if I look at the synthetic analog of KO and I kill tau, then this is exactly the E2 page of the, if I take homotopy groups, then this is going to be the E2 page SF of, well, a priori, it's the Adams-Novikov spectral sequence for KO. And then I told you as well that this is the same as the E2 page for the homotopy fixed point spectral sequence for Ku with this complex conjugation action. Okay? And now this is just really straightforward to prove, to do this long exact sequence argument. And I want to write down some of it. So I want to use some colors. So I'm going to use a red and a blue. The blue is going to come from this part, and the red is going to come from this boundary map. with some shift. Okay, and what is this going to look like? Well, okay, well, I just run long exact sequences. So here is the E2 page of the homotopy fixed point spectral sequence associated to KO here. So here is degree 3, here's degree 4. I have this class. I have eta, 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 eta. And then, well, what's going to happen with this boundary map? So the degree that this boundary map shifts by moves this blue picture here and shifts it up by 1 and to the left by 1. So it means it's going to start with something here. And this guy's going to move up. This guy's going to move up. We continue like this. And this guy's going to move up. I'll explain this in a second. This guy shifts, this guy shifts, this guy shifts, this guy shifts, this guy shifts. Okay, very good. And there's, of course, more to the left and more to the right and more up. But let's be satisfied with that. Okay. And so actually, I want to point out two interesting things. The first one is all of this blue stuff here is stuff in the kernel of this map on the E2 page. And all the red stuff here is in the co-kernel of this map, but now shifted up by 1 and to the left by 1. So in particular, all of these torsion classes are in the, they're 0 on this under this operation here, so they're in the kernel and the co-kernel. So we get all of these dots that appear and sort of checkerboard the whole picture. Notice that this class actually dies. So in the homotopy fixed point spectral sequence in this homotopy fixed point spectral sequence, the one in blue, we should have a class here in degree 4 that ends up supporting the famous D3 here, because we know that Ku in degree 4 is generated by Z. So, but this class doesn't survive. It's not in the kernel of this map, because on torsion-free things, this map is injective. So it means that everything in filtration 0 from the blue class has vanished. So this is gone. And there's actually nothing in filtration 0 except for this class here. Everything else in filtration 0 has vanished. And so I said that this map on torsion-free things is injective, and in this degree it happens to have a co-kernel a Z mod 8, which is why the Z mod 8 pops up from what was a Z here. Okay? And now you can compute, so now I've given you the E2 page of this spectral sequence. And now you can do whatever you want with it. You could say something like, well, I know that the blue things map to the classical atoms, the homotopy fixed point spectral sequence for Ku under this map. So I could pull back like the classical D3 that lives here to a D3 here. Or I could make one of these nilpotents of eta arguments. I could spot eta here and then argue that eta to the 4 has to die, so something has to kill it. Either way, you end up with a whole bunch of differentials like this. And good, I wrote them down. A whole bunch of interlocking differentials like this. And you can compute the whole spectral sequence very, very easily. So this leads to let me, rather than saying that leads to a whole computation, let me just say that it collapses on E4. Okay. So how do you use this technique to actually show detection? This is the second trick that I want to highlight here. You have to remember a little bit about periodic homotopy theory. So how do we define sort of V1 to the 4 infinite families? Well, what we do is we say something like, let's have a look at, we say something like, yes. So I have a whole bunch of alpha families, this alpha 1 plus 4k. These are the guys that are detected by eta beta to the k in pi 8k plus 1 of ko. So these are guys that end up being detected in ko, but let me prove from first principles that they're actually detected in j. Okay, so what do? Well, we can look at where these guys live in the E2 page of the Adams-Novikov for the sphere. Well, by definition, they are the image of a whole bunch of V1 families. So they're the image under the boundary map k plus 2 in degree 0 of synthetic sphere mod 2 tau, and I'm also killing 2. So this is the definition of these maps. This is the definition of this alpha family here. Is this the image of these V1, these powers of V1. Okay, so there's this Hurewicz map that goes down to this signature spectral sequence for this J spectrum. So I have pi 8k plus 2, 0 of J mu mod tau 2. I have this boundary map, goes to pi 8k plus 1, infiltration 1 of J mu mod tau. And I want to prove that these guys are non-zero. So let me just write that as a sentence. I want to show that h of alpha 1 plus 4k is not equal to 0. So how might you do that? Well, this h alpha 4k is the same as, well, we know that alpha is defined by the image of this guy here, and this diagram commutes, so this is just the same as partial applied to h bar of v1 to the 1 plus 4k. And so in other words, I want to show that, and this guy here is sent to something non-zero. So it's pretty clear to see that this guy is sent to something non-zero because you can map all the way down to ku either. Yeah. And okay, so all I need to show that this thing is non-zero is to show that this partial map is injective. Okay, so how do I show that something's injective? Well, this partial map is a partial map in a long exact sequence associated to a cofiber sequence. So let's just write that down. It comes from map pi 8k plus 2, 0 j mu mod tau. But the only thing I told you about this E2 page of this signature spectral sequence for J, the only generic thing I told you was that it doesn't have anything in filtration 0. Because all of the filtration 0 stuff comes from torsion-free stuff, and all of this is not in the kernel of psi3 minus 1. So in particular, this group is dead, and so this map in our exact sequence is injective. Okay. This is a super cute trick, and you can do it all the time, and somehow J is designed to make this trick work as well as possible. The fact that you've killed everything in filtration 0 means that every time you run an argument like this for a different type of alpha family or like these mu families and stuff like this, you're always going to have a very easy argument because you've killed everything in filtration 0. So just to wrap things up, I just want to mention some results at height 2. So at height 2, one can replace KO with TMF, obviously. So here is, I just want to mention 2 theorems proven by me and Christian. So the first one is that one can compute the Hurewicz image of the fiber of psi2 minus 1 from TMF, and now we're working at the prime 3, so I've changed my Adams operation. Not only can you compute the Hurewicz image of this fiber, or at least can compute almost all of, there's a slight discrepancy. So we can compute all of the Hurewicz image of this fiber and produce new infinite families in the stable homotopy groups of spheres at the prime 3. So what do you do to make an argument like this? Well, you take TMF, you look at the synthetic analog of TMF, you then open up a book or a paper that tells you how to compute this Adams-Novikov spectral sequence. You look at the E2 page, and you take the fiber co-fiber by psi3. You have to work a little bit harder because you're not just working with alpha family, but you're now working with beta family elements, and you need to make 2 of these short exact sequences. But I mean, we're working with spectral sequences, so every time we reduce something to a short exact sequence, we should be pretty happy with ourselves. Actually, maybe just let me erase this half. So this is actually a very, very naive thing to do because there's no way to hope that the Adams operations on TMF detect everything, all of the sort of V2 periodic families. For something like that, you want to work with Barron's QN spectrum. So let me just write that down quickly. So Barron's defines something which he calls, I'm just going to work with Q3, which he defines as a certain limit. And just like J is defined as a certain equalizer, this Q3 is defined as some sort of 2 equalizer. We have TMF. You have TMF, and you put some sort of level structure here. And you have TMF with level structure. So just in the same way that an equalizer is like the 1 truncation of a cosimplicial diagram, this is like a 2 truncation of a cosimplicial diagram. And one thing, yeah, I just want to state that so Hopkins Moholt studied V2 to the 32 periodic families at p equals 2. And to do this, they use TMF. There's also a paper by Bobkova, Bhattacharya, and Quigley, where they use TMF to construct even more, to construct more periodic families. So these guys construct 7 new V2 to the 32 periodic families. In the sphere. But the cool thing is that if you do what I've been doing the whole time in this talk, and rather than trying to compute a spectral sequence of something difficult, you rather take your limit or co-limit, import the whole diagram to synthetic spectra using a synthetic analog, and then take a limit or co-limit there, and then do a computation, then you try to reap the rewards from that. So this is the final theorem I wanted to write down, is that me and Christian have found, have discovered / recovered, so discovered some and recovered others, at least 25 new periodic families. Which seem to, which do totally absorb the Hopkins-Moholt results, but of course we're using very similar techniques. We're using TMF, and they also seem to absorb the BBQ results, but it's a bit hard to check because their results are a little implicit. Okay. So I think the one takeaway from this is that, you know, rather than trying to compute a complicated Adams-Novikov spectral sequence for a complicated spectrum, it might be much easier to just compute the limit in synthetic spectra and then try to compute the signature of the associated spectral sequence. Okay, that's all I have to say.
Questions? What counts is, so in the Hawkins small paper, there are some classes that are detected directly by the Hurewicz mapper TMF, so there's sort of in the Hurewicz image.
Yeah.
But I think they also discuss some more classes.
Yeah.
So what counts as more and what counts as new here?
Yeah, it's a good question because, I mean, I would really like to know a little bit more about like how much we take this very rough draft as on faith. But I mean, so what they roughly do is they do roughly produce the Hurewicz image of TMF, which is of course, we take that as known now from Behrens, Mahold, Quigley, and also from you and Bob. And actually, a lot of the classes that they discussed that are not in the Hurewicz image of TMF, but are V2 to the 32 periodic families, things like kappa bar, eta cubed, or something like this, which are not in the Hurewicz image of TMF, but which they do show are V2 to the 32 periodic, do actually appear in Q3. Q3 has a really rich Hurewicz image that seems to detect a lot of things that you can prove exist using TMF, but which just directly exist using Q3. And then you can take some of the techniques that they used to sort of go away from the Hurewicz image of TMF to try to go away from the Hurewicz image of Q3. And now we're getting real sticky. It's getting complicated.
So you look at these 25 things. Is that because that's all that can be seen using synthetic spectral, or is it because that's just as far as you went, or did it get too hard, or what stops you?
Yes, all of the things are true. I mean, so no, this is not the limit of what can be done. Like there's sort of a very canonical, somehow for us, there was a very obvious family of, a very obvious collection of families that were detected by Q3, and there's exactly 20 of them. And then there were 5 extra guys that we could see in low degrees that we were like spotting with our hands and being like, oh yeah, this works. And then at some stage it got too hard. So like, it's a bit hard to think of how to actually summarize the results too. Like, do you stop at some stage because it's too hard? I mean, I think we will, but I don't know. It would be good to have some help on some of the. Yeah. Because it definitely does more, but it's a bit hard to even describe what's coming from the sphere. Yeah.
It's all of period 192, or are there also larger periods?
They're all of period 192, and yeah. I don't have anything. There's nothing. At least the techniques that we're using are always going to. It seems like they're always going to produce V2 to the 32 periodic things. I don't think we can get anything with higher period, or at least that hasn't come up at all.
It's in the image of J part, I mean, there if you were looking at four torsion and so on, you would also see things of longer periods. So
Yeah, but
depends what short exact sequences you're using.
exactly. And I mean, all of the things here are, a lot of it is 2 torsion. And the things that are like 4 or 8 torsion, like coming from kappa bar or things related to this, all just happen to be V2 to the 32 torsion. Sorry, V2 to the 32 periodic. Yeah.
Any other questions? So let's take a break again.